So next we'll be starting with the explanation of a few problems uh, that are based on the principles that we have learned in the previous lecture. Now this is the first problem. Here we can see that the problem given is three 11.2 kilovolt generators are interconnected as shown in the figure by a timer through current limiting reactors. So three 11.2 kV generators are connected together to a timer through current limiting reactors. So these are the current limiting reactors. They are connected together at a timer, and obviously this is the output path through the circuit breaker. This is the feeder impedance. So you can see that from here. A three-phase feeder is supplied from the bus bar of the generator A at a line voltage of 11.2 kV. So this feeder is supplied by generator A. There is a little bit of mistake. This is generator A. Consider this to be generator B and generator C. Let me see. Yes, consider this to be generator B and generator C. I have written all A's. It cannot be all A's. So this is the generator A, this is B, and this is C. Keep that in mind. Three-phase feeder is supplied from the bus bar of generator A at line voltage of 11.2 kV. Impedance of the feeder is 0.12 plus J 0.24 ohm per phase. We have to compute the maximum MVA that can be fed into a symmetrical short circuit at the far end of the feeder. So okay, now it is better. So we have got the problem written here. Three generators uh, which has a voltage of 11.2 kV. The feeder impedance is 0.12 plus J 0.24 ohm. So we have to find out the per unit generator reactances. So XAG is equal to, all of these at 8%. So they will be, all of these three will be 0.08 per unit. Now reactor reactance that is given here, we have got, sorry, in the question there is a mistake. Reactor reactance is not given, but let us take, we'll take the reactor reactance as 10%. So it is 0.10 per unit. Feeder impedance we have got as 0.10 plus J 0.24 ohm. Next we have to choose a base. So we choose a base of MVA and KV. So 50 MVA 11.2 kV. Base impedance will be given by V square by P. So ZB is equal to 11.2 square by 50, that is 2.5088 ohm. This is our base impedance obtained from the base MVA and base KV. Now we have to convert the feeder per unit value of the feeder that is already given, or rather we have to convert the ohmic value of the feeder impedance to the base per unit value. So to divide the actual ohmic value by the base value. So doing that we get this value 0.0478 plus J 0.0956 per unit. Now the base values or voltage values, see all these generators have the base voltage or the voltage of 11.2 kV, which we have selected as the base voltage. So base voltage is okay. Now what we are doing is we are applying the formula of converting one per unit value to a new per unit value, that is a per unit value which was calculated at a previous base MVA and base kV or base voltage, and we convert it to a new per unit value at a new base MVA and new uh, base voltage. So here as the base voltage is remains the same, so it will be 11.2 by 11.2, that will be 1. So we only have to take into consideration the base MVA. So for XA, the generator A, the MVA was 40 MVA, so we have to convert it to 50 MVA. So to multiply the old per unit impedance value by 50 by 40 to get the new per unit impedance value, that is J 0.10 per unit. For the second generator, that is generator B, we have the voltage of the generator as 11.2 kV, which is equal to the base voltage, and also the MVA of the generator is 50 MVA, which is equal to the base MVA. So we have to do nothing for that impedance. Again, for XC, that is the per unit impedance of the third generator, generator C, that we have to multiply by 50 by 30, 50 divided by 30, and that will give us the new impedance value, that is J 0.133 per unit. Similarly, you have to convert XA, XB and XC. These are the reactance values, the current limiting reactor values. You have to similarly convert them to the new per unit values. Now we have to assume a zero pre-fault current, which means that no load pre-fault condition, or rather in the no load pre-fault condition, the current was zero. Or rather, yes, if there is no load, the current will be zero. The circuit model of the fault calculation is as follows. You can compare this with the actual diagram above. You will find this is the circuit model. We have put all the impedance per unit values that we have calculated. We have put them here, and this is our fault current. This is the point of fault. This is our fault current. So we simplify the circuit. After simplify the circuit, we get this. We find out Z, which is the combination of these two parallel reactances and this impedance in series. So we get Z. So short circuit MVA is equal to, if you remember the previous formula, then short circuit MVA is equal to V0 into IF into base MVA. So IF is equal to V0 by Z. So this V0 by Z, that gives us IF multiplied by base MVA. So this is our short circuit MVA. V we have taken as 1 angle 0. So V0 square will be 1 square by Z, which we have found out here, the polar value. So 0.1727 multiplied by 50. Here we do not need the angle. So this is our base MVA, 289.5 MVA. Next, we have a few more problems. Here two generators G1 and G2 are rated at 15 MVA 11 kV and 10 MVA 11 kV respectively. The generators are connected to a transformer as shown in the figure. You can get the details of the transformer here. We have to calculate the subtransient current in each generator when a three-phase fault occurs on the high voltage side of the transformer. That means this is our high voltage side. This is the 11 by 66 kV transformer. 11 kV is the low voltage side and 66 kV is the high voltage side. So our fault occurs on the 66 kV side. We have the subtransient reactances of generator 1 and generator 2 and the reactance of the transformer. So we choose a base MVA of 15 MVA because we have both the transformer and this one generator at 15 MVA. So we take this as the base MVA. Obviously we have to convert this per unit value of the reactances to the new base, new per unit values with the new base. Then we are putting this is a fault point on the high voltage side. We are putting the value of the reactances. The voltage will always be 1 angle 0 degree, as we have seen in the previous slides, where it was the method was explained how these calculations are done. So 1 angle 0, and then we simplify and we can find out IF. So when we find out IF, we can use the current divider rule to find out Ig1 dash dash and Ig2 dash dash. Then we find out the base current and multiply the per unit values with the base current to get the total values. So like this, a few more problems will be given in the problem sheet, and then the assignment will be given. So I hope that you will be able to do the assignment, and you have to submit the assignment within the due date. So In the next video, we'll be continuing to the study of unsymmetrical faults. So for today, this is all, and we have done most of the part of symmetrical faults. So next day we'll be moving on to unsymmetrical faults.